Now, one comment that was made over the break is that there are some funny things with these data in that the porosity is not decreasing so much with depth, indicating that the bulk density may not be increasing so much with depth. These soils are a little funny. They are forest soils. This is from the H.J. Andrews Forest in western Oregon, and these are andesols developed on volcanic terrain, and there are some slight peculiarities with these soils. But be that as it may, this depth decline in drainable porosity is a fairly common feature. It's just that normally there's more of an increase in bulk density with depth that we might see. But the key thing to kind of take away from this is that this depth decline in drainable porosity, its shape function can be derived from measured data. So you're working at a site in the Tongass National Forest. You can go out, take cores down through the soil profile, compute the moisture release curve for those soil cores, and then that is going to give you bulk density at those different points where you've extracted the cores and allow you to define that depth decline in drainable porosity. Here's saturated hydraulic conductivity data from a number of sites. This is again showing depth functions. This is saturated hydraulic conductivity, where we've taken a core from the field, brought it to saturation, and computed the permeability. These are some summary statistics here with kind of box whiskers descriptions. So this is in centimeters per hour. Some of this is from the Andrews, from data by Rankin and Haar. Some of it's from a grassland site in Switzerland where we've been working. But it's showing you, again, this general decline in hydraulic conductivity with depth. And in fact, when Bevan and Kirkby developed Top Model, they used this Rankin and Haar data from the Andrews as the data to kind of define this depth decline in conductivity with depth. So one thing to not forget, and this is what I referred to earlier, is that when we talk about saturated hydraulic conductivity, we do need to keep in mind that while saturated hydraulic conductivity is an important measure and is really critical often for turning on lateral flow on the slopes when we get zones of positive pore pressure that might develop, when we begin to desaturate the soil, the hydraulic conductivity drops really steeply. And we can have situations that might be counterintuitive where seemingly less conductive material could have a higher permeability at a given water content or a given matrix potential or tension. It's just a small reminder here for that. Now, in terms of bulk density, one of the better instruments I think that one can use is what's used a lot in Japan. It's a comb penetrometer. They call it a knocking pole penetrometer. And this is a device, you might have used this in your studies, particularly if you're coming from a soil mechanics or civil engineering background. But essentially it's a 5 kilogram weight that is dropped from a known height onto a disc here that you can see. And you count the number of knocks it takes to plunge the rod vertically through the soil profile. And not surprisingly, you drop the 5 kilogram weight and you first start out at the surface. This is up at the Maybe-So catchment in southeast Alaska. The pole goes quite some ways into the soil. But as you go deeper and the bulk density increases, now you might need to drop that 5 kilogram weight several times to have it move, let's say, 5 centimeters vertically through the soil profile. So here are some data from that particular site. This is soil depth down to 1.4 meters. Here we're seeing the kind of bulk density decline with depth, 2 little increases in bulk density. Maybe these are small impeding layers in the profile. And this happens to be the soil-till interface, where we have, this is a till mantled site at the Maybe-So Forest Service watershed. This can be very helpful, not only for helping to quantify some of these depth declines in key soil materials, but also defining an interface, something really dramatic like the soil-till interface, which can be very important for turning on lateral flow that we might see. And there's an abundant literature, unfortunately it's all in Japanese, but it correlates these knocking pole data with bulk density, hydraulic conductivity. There's really an exhaustive literature on how this very simple measure correlates with important soil properties. We've used this a lot as a way to verify what we see from ground penetrating radar. If you've used GPR at all, there's often a bit of geopoetry associated with defining what the soil depth is or where impeding layers might be, and this has been a useful technique for that. But if we try to summarize this matrix aspect of the plot scale, really it boils down to this. We have, this is a very conceptual way of looking at this, by the way. We have an unsaturated zone and we have a saturated zone that may be quite transient. There may be times when we have no saturation in the profile, and there may be times in an event where we have saturation that's developed for some hours or days following a rain event. We have a porosity, and the drainable porosity decreases with depth in some way that we can quantify with measurements. Z is the total soil depth, and this drainable porosity with depth really is defined by a shape function that we can derive. These are some of the important issues at the plot scale. And then similarly with hydraulic conductivity, K sub O there, it also has a decline with depth that we can compute, either by taking soil cores, bringing them into the lab, or better yet, going out to the field with a well permeameter where we measure in situ hydraulic conductivity. And this lateral flow then is really occurring not in the unsaturated zone, even on steep slopes, but it's in this transient saturated zone. It could be a water table in the till rising into more transmissive mineral soil, saturating this and generating lateral flow, as we'll see as we move to the hill slope scale. Or it could just be water perching at an impermeable horizon, generating saturation, and then the subsurface flow really being a function of these things that we talked about before. Beta being the slope angle, W being the depth of water, or the height of the water table, and T being the transmissivity. Now, against this backdrop of matrix conditions at the plot scale are the preferential flow components. And this is rarely addressed in the kind of hydrology texts that we look at, and variable source area theory and a lot of our widely held mechanisms don't look at preferential flow in detail. But this really does control the behavior of our forest soils when things are wet. And what we're going to look at are everything from the distinct macropore that we might see that could be a discontinuous decayed tree root or some feature in the soil, to maybe more mesoporosity, which is something maybe between the extremes of the matrix, the micropores, and the macropores that we could see and measure in the field. So we're going to spend now a few minutes looking at preferential flow. And the point I really want to make is that it's very network-like. When we do dye staining studies in forest soils around the country, what we see is often something like this, that water infiltration vertically, despite our known, assumptions about wetting fronts propagating vertically through the profile as we wet up the soil surface and we might have a wetting front advancing. This is matched by deeper, more preferential penetration with depth through this kind of flow network. And often these macropores, at least in the upper decimeters of the soil profile, are rather network-like and interconnected. And, this is the best hydrology humor gets. Darcy wouldn't like this because this kind of is a problem for Darcy or Richard's equation, our standard equations for flow in porous media. We're saying that this is something really different to the Richards equation, which is our main equation for deriving infiltration with depth, because this is the reality of it. I think I showed you this slide earlier. This is a dye staining study at a site in Switzerland, but here you're seeing the blue dye that's penetrated after we've irrigated the surface at a rain intensity characteristic of this site, and then we've exposed the soil face, so we're looking side on now, or face on, and this is an image analysis of what the preferential flow might be. Now, this is important because, as we said earlier, we get this strong depth decline in drainable porosity, which really is defining our storage. So all we need is a bit of preferential flow to get some rainwater down into this zone, and this is what can flash saturation on in ways that would be very, very difficult to explain with Darcy-Richards kind of theory. Because Darcy-Richards would be saying we would have this, this flux of water vertically through the profile controlled largely by capillarity and gravity. The macropore flow vertically, preferential flow, is certainly controlled by gravity but not capillarity. This is moving through non-capillary void space, and that's why this is a real problem for this kind of Darcy-Richards way of looking at infiltration. Now there's two aspects to this. There's the initiation of macropore or preferential flow. You saw in the hydrophobic soil that if we create impermeable conditions at the surface, that microtopography can actually result in funneling effects to generate concentrated points of seepage. The same can happen in non-hydrophobic soils where there are some irregularities in the soil surface topography that create zones of preferred infiltration or initiation points. Then the other thing is the interaction between preferential flow and the matrix. There are many conditions where you might have preferred flow in a really tight, clayey sort of soil matrix. Maybe you're in the near stream saturated area or in an area characteristic of a variable source area with some kind of clayey soil. One could have preferential flow features in that kind of setting where there's very little interaction maybe between water moving in these preferred paths and the surrounding matrix. Or you could have preferential flow in a much more well aggregated material, and there could be quite considerable interaction, both from the macropore out to the matrix and vice versa. These preferential flow paths can be formed by a variety of features. It could be voles and moles in an agricultural setting, maybe enhancing soil drainage for their own kind of cycle. It could be plant roots, decayed, living. It could be cracks and fissures in the soil. If you've got high montmorillonite clay content in the soil, that might experience some seasonal cracking. And natural soil pipes. These are things that might be, decayed tree roots, perhaps along an interface, that are enlarged through alluviation or other kind of soil forming processes. The key point is that, and this is why the fact that they make up only a small percentage of the total porosity and yet are so important for controlling most of the flow at or near saturation, is Poussil's law. Poussil's law tells us that the flow in a pipe is proportional to the fourth power of the pore radius. So just think about that. You get a couple of big honking pipes in a close to saturated media, all the flow is going to be there, relatively speaking, compared to the matrix with this fourth power relationship. This is a change in pressure along the flow path. This is the length. This is the viscosity. It's not an equation you need to remember necessarily, but just this fourth power control is really profound. So if we were to go outside and dig a pit and do a dye tracer experiment, let's say a couple of meters from the hotel here in some undisturbed soil, this is what we might see. And again, I want you to kind of reflect on this in the context of what we've talked about in terms of matrix changes with depth. This is now superimposed on those matrix changes with depth. It also presents a problem for how we measure things. When we go out to forested catchments and use tensiometers, TDR rods, any kind of point measurement when we're inserting something into the soil and making a measure, we need to be very aware that where we input our point measurement device, really what it's representing. And it may not be representing the mobile water that we want to sample. This is especially true for, say, a suction lysimeter. You're interested in, say, flushing of dissolved organic carbon or nitrate at your site. And you put a suction lysimeter at different depths through the profile. You're quite likely not sampling the mobile water that's contributing to the flushing on the time scale of an event with that kind of sampling regime. You might be getting a good representation of the soil water end member between events, but what's happening during events is really through these preferred flow paths. Here's a a visualization of this process. Marcus Weiler is a former postdoc of mine, and this is part of his PhD work. This is going from the soil surface down 1 meter. Those are water content changes measured with TDR rods placed horizontally in the soil now. So these are rods not integrating over 0 to 30 centimeters like we talked about before, but inserted at 10 centimeter increments down through the soil profile. And this is something that you might see in a typical experiment. Again, we're talking about 1D at the plot scale. Here's the wetting front propagating vertically through the profile in this kind of Darcy-Richards-like way. And now you can see this is a visualization now of the dye staining that I've showed in some earlier slides. And you can see then the preferential flow behavior. This is a vertical slice, so this isn't just magically appearing here out of thin air. This is maybe some kind of tortuous flow path that's gone in and out of that vertical plane where we've sliced this particular soil. And it's pretty tough then with measurement techniques that exist today to give us a representation of that. You know, our TDR rods aren't really doing a good job of detecting this kind of penetration. And again, this is the hot spot for very little storage, and that's why this matters so much. This matters as well if you're, I don't know, siting waste disposal facilities, if you're siting a landfill, if you're at the INEL site in Idaho and you've got trenches that are filled with low-level radioactive material, gowns and gauze and gloves and things. They're often excavated down to 20 feet, throw in the low-level radioactive stuff. It's often lacustrine clay, low permeability material. Fill it back up with that low permeability material, tamp it back down again, and leave it for 1,000 years. That's fine, because it's a very dry environment, and the regional water table's, you know, hundreds of feet down perhaps. But over time, and with vegetation development, because the vegetation is often the key kind of driver of macroporosity, these are some of the issues that people are concerned about. There was a question, I think. Yeah, I think it was 60 millimeters an hour. That was pretty high. And clearly, some of these effects are related to rainfall intensity. But that was characteristic of this particular site where the sprinkling was done. Now, this is not a new concept, and I just want to make you aware of this fact that here's a paper in 1898 where a sanitation engineer, as they were called back then, is saying that cracks 1 and 2 inches wide and 5 feet deep are sometimes met with, and it has been found that these are intensified in drain land with the result that direct passage of sewage and surface water into them has occurred on sewage farms of this nature, so as the effluent is not purified as intended. In other words, you know, people have been aware of this for some time. We did a lot of work on fate and transport of septic effluent in the New York City water supply, and this was a real issue for determining setback distances between septic leach fields and live stream channels. Because when you go to any individual septic system, it was kind of unique. It was in its own soil setting, it was on its own topographic position, and each one was somehow behaving quite differently. And it was largely due to some of these kinds of issues. However, when we started to look at the whole catchment scale and look at the relationship between septic density and, say, low-flow nitrate concentration, something that's indicative of what's in the septic, you see a very, very strong correlation as you begin to kind of get to a scale where these features start to make sense. So this is one kind of issue that we can't put so much emphasis into this little tiny plot scale because you have great difficulty upscaling a 1 by 1 meter soil plot to the catchment. A catchment isn't a linear superposition of a billion 1 cubic meter soil chunks. You know, a catchment or a watershed is really made up of larger landscape units that connect and disconnect. So we don't want to obsess about these complexities too much, but what we want to take away from it is the fact that we have these known declines in matrix characteristics, and we have these known penetration of event water to depth, and the two conspire to give us this rapid development of positive pore pressure. Here's some more data. I just show you one or two more slides. This is now a series of TDR rods going from the beginning of this wetting event through to about 2 hours. These TDR rods are installed horizontally at these different depths down through the profile. And this is showing how the TDR is measuring, because they were installed in this area, this kind of center of mass of preferred water movement to depth, but of course are not seeing what might be happening elsewhere along this area. This is kind of the representative elementary volume concept personified, meaning that, if this was our soil core and we extracted this soil core from anywhere in the profile, we would say that this volume is not capturing the full range of behavior of that environment. This isn't representative of the continuum of pore size characteristics in this soil setting. Maybe even a meter by a meter by a meter is not a representative elementary volume of this particular system. And if we're focusing on processes that are below that representative elementary volume, then we're kind of in the noise, meaning that we could have great heterogeneity if we try to focus on small chunks of the system. What we need to do is kind of aggregate to a larger piece of the system to understand better the behavior. I'll talk about that a little more in terms of catchments as well. This REV concept that you may have heard of is also taught in the watershed literature. We spend a lot of time in forest hydrology working on little headwater catchments of 1-10 hectares in area. But whether that is representative of the continuum of watersheds within our larger, say, 10 square kilometer basin, it's the same kind of concept. Just while I'm on this, let me tell you what I mean here. Let's say we've got a watershed. So we're talking about REV and REA. What I refer